Hello everyone, welcome to my video. And today I'm delighted to talk about a breakthrough in fraud detection via reinforcement learning. But before I tell you about these reinforcement learning agents and this trial and error method, how it works, please go through this and then I will explain in a very simple manner.
How is it possible for AI to make decisions in unpredictable environments? The answer is reinforcement learning. Reinforcement learning shows up in all sorts of real-life applications, like robotics, playing complex games, and autonomous driving. Essentially, reinforcement learning is the science of decision-making. It's about learning optimal behavior in an environment to obtain maximum reward. Optimal behavior is learned through interactions with the environment and observations of how it responds. The main elements of a reinforcement learning system are the agent or the learner, the environment the agent interacts with, the policy that the agent follows to take actions, and the reward signal that the agent observes upon taking actions. Reinforcement learning can solve complex problems that cannot be tackled with other machine learning algorithms because it focuses on the problem as a whole, does not require a separate data collection step, and it operates in dynamic, uncertain environments.
Okay, so I will explain step by step now. So, firstly, let's go with the highlights. So, the use case is of same credit card fraud detection. I mean, the credit card data file that we downloaded from kaggle.com, and this time we will use reinforcement learning agents to classify it as fraud and not fraud, and that is the same file I lastly showed the performance of our stacked artificial neural network model. Okay, let me show you. See here, you can see here that last time when it I ran that model, so this was the performance mass metrics. It was able to recognize 491 fraud transaction out of 492. Only one was left, and there was 14 false positive. So what's happening right now? Uh, right now is that we will compare those stats. Firstly, what is our this model? This is a reinforcement learning model based on trial and error method. I will explain. Firstly, you should understand that this is also a stacked model. Means two RL agents are there, primary and residual, and plus XGBOOST is a meta model, final model. So what happened is that I showed you artificial neural network. That is also I have fine tuned, and there is one more model to compare, CNN model. CNN model is convolutional neural network model. These are used to process images and recognize images. But I have converted this to fraud model as well. So we can convert any model to the fraud model because it's up to you that how you use that model. And sometimes some models possesses extraordinary qualities. So the comparison will be on the real credit card dataset. I told you that is from kaggle.com, and that was a real telecom. I mean, a real bank. Credit card transactions. Then there is bluff transaction as a dataset that I have created. We will check how all these models work, predict on bluffed transaction dataset. These are some transactions that in which some real transactions are there, but plus some transactions are being changed. That if fraud pattern changed, then what happens? So another highlight is RL alerts demonstration. So reinforcement learning alerts demonstration also is there. We will use Python and we will generate the alerts through RStudio. And there is a very in-depth analytics. Please stay tuned for that. And the future of our roadmap is I will show you how we can further, using unsupervised learning algorithm isolation forest, we will use with the RL agent ensemble. This is our future roadmap. So that's it. Let's move ahead. Okay. So yeah. So We are, moving beyond traditional methods to a dynamic intelligence system powered by reinforcement learning. I will show you how we are achieving, this unprecedented accuracy, and most importantly, how can we secure our financial systems against the, these unseen threats and sophisticated, and unseen threats. Yeah, I mean, yeah. So, yeah, and you can see in the slide the evolving threat. It says so. The problem is that fraudsters are not static. Means they are not constant. They are constantly evolving their techniques. So our traditional models like ANN and CNN, I just told you that I will show the comparison, and even machine learning models, they are passive learners. They are trained on historical snapshot of data, and they are rely on thresholds, as I have showed in earlier videos. They are excellent at what they were trained to do, but when a new fraud emerges, new pattern emerges, these models fall short. This leads to two critical problems: missed fraud, actual fraud that is missed, which is direct financial loss, and false alarms. And the false alarms, customer dissatisfaction, and a lot of time, operational time got screwed. So next slide. Okay, so I was telling you about passive and active learning. So I told you these ML model, ANN or CNN model, these are passive learners. Okay, so you can see here in the slide itself. This is the stack of books. So what happens is passive learning is like what these ML models or these ANN or CNN models do. There is already a book, and we feed this data to them. They are trained on this data. They cram this data. And another side, this is active learning. This is our reinforcement learning model agent, or I will say. So reinforcement learning, trial and error. When you are playing a live chess, a game of chess, and that is active learning. So that is the main difference. So what we see is as an active learner, instead of just looking as a historical data, the system is like a chess grandmaster. It learns by playing the game, making a move or a decision, and then receiving feedback, either a reward or for the correct decision, and penalty for a bad decision. And then what happens? This reinforcement learning system adjusts the strategy in real time. This allows our system to adapt to new transaction dynamics and make decisions based on context, not just static rules. So what happens? I will tell you in a very simple manner. The data, that credit card data, will be fed to the reinforcement model 500 times, 1000 times. Firstly, it will make random decisions like this is fraud, this is not fraud, this transaction is fraud, this transaction is not fraud. Then slowly and slowly it will learn that my decision was wrong. Why? Because they are the heavy penalty is being applied on me, minus 1000 point, minus 2000 points next time. Similarly, if I'm making a good decision, I'm cutting the fraud, I'm classifying the fraud as fraud, then rewards are there, I'm getting plus 1000, then again plus 2000, like that, like this. Okay. Okay, so as you watched the clip, in the beginning, it was stating that how these RL agent, work. So there is environment, and the environment is the endless stream of credit card transaction. I told you this will go by 500 times and 1000 times till we got our desired precision and recall rate. So this is the environment. The transactions will keep going. The agent, this is our agent, RL agent, reinforcement learning agent, our learner. So in this context of our fraud detection system, this is our intelligent fraud detection system, learning to make the best moves. Means fraud or not fraud. So the state, and the state is the transactions characteristics. I mean, what is the features? There are a number of features, as you know. Merchant name, IP address, amount, time, day, night, and other feature as well. Okay, so that is what the agent sees. And the action is fraud or not fraud. What the action, agent is making. The policy, I told you, this is the playbook or strategy for making these decisions. I mean, how you are giving reward to the agent, or giving penalties to the agent. Are you making high penalties, very high penalties, rather than good reward? Because we cannot miss the frauds at any cost. So these rewards and penalties for correct decisions, catching fraud, and approving legitimate transactions. There is a reward for the agent and penalty, as I told you, for incorrect decision, missing fraud, and creating false alarm. We will penalize the RL agent, reinforcement learning agent. So this direct feedback mechanism is what RL learns, reinforcement learning agent learns to optimize itself, minimizing financial loss and customer impact. Okay, so I have told all the elements of this RL model. Let's go ahead. Okay, so this slide will tell you, this is a little bit technical. I will go in a very simple manner, and but just listen what I'm saying. This is deep Q network. This is the brain, as in showing in the picture. Okay, so and then there is memory called experience replay, and there is some epsilon decay. Okay, so these are the components of RL agent's brain. Okay, so I will tell you now that the how the training goes. So firstly, the thing is that it is the process is called exploration versus exploitation. So what happens is, agent has no prior knowledge. At start, agent doesn't know which action will yields the best rewards, because initially the agent has to move towards the higher rewards. Then only it will be a good model, right? When it will judge, it will be par excellence, excellent on judging fraud versus not fraud. So at starting, it doesn't have any knowledge, like any child, or like any a new learner. So it goes for exploration phase, when it randomly choose the action. This is fraud, this is not fraud, this is fraud, this is not fraud again. So that environment that I told you, the and what is environment? The endless stream of credit card transaction that will keep going, and it will keep making the decision: fraud, not fraud, fraud, not fraud. And then rewards and penalties will be there. So the goal is to gather information about the environment. I told you, the endless stream of transactions. So what are the possible actions and their outcomes? So it will learn that last time I was wrong, last time I was right about it. Through the state are, I told you, the transaction features, different n number of features are there. So these are methods that it will take. So then when it learns that after ample time, then it goes to exploitation phase. So what I will tell you, with a simple, very very simple example, that uh, treat like a kid is having a jar of candies. The kid gets a new jar of candies, but in that candies, there are red candy, there is purple candy, there is green candy, there is white candy, and the kid doesn't know which candy tastes good. So what happens is, It will firstly it will check all, it will go for random decisions, right? Similarly, in our as our RL agent, the child will choose any candy and will taste. So at the beginning, the child picks randomly, and trying different color of candies to learn which ones are good at taste. This is like high Appleson decay rate, we can say in term of technical term, like we can set initially to 90% or more. So then what the story becomes, the story becomes like that the child is saying that 90% of time I will try something new. Why? Because I don't know which candy is best. Okay, this is the exploration phase, as I told you. Random decisions by the agent itself, but whether it is fraud or not fraud. Then come the exploitation phase. So means low epsilon. Exploration was high epsilon. I told you it was. We set it, around about 90% or more. Now this is exploration phase, that is called low epsilon decay. So after many times, the child learns that red candy is the best. So now the kid mostly pick red candies. Uh, so this is like having a low epsilon decay of 10%. So now what the story becomes, that 90% of time I will go which is best for me. Okay. Now, so this is how it got transitioned over time, that from exploration the agent goes towards the exploitation, because it through rewards and policies, and it learned that which is the best decision. So that was it regarding the epsilon decay. So what is DQN? You can see in the slide itself, it is a brain. So the smart brain, it because it has neural networks. So I will give you another example. See, if there is a gamer who is playing a game, and that game has based on maze. Maze has a trap, and the theory is like that. When I'm near a trap and I go left, I usually survive. So what happening is right now, this Q network, the DQ network is it mapping the situations. Okay, these states to smart actions. States, I told you, that has transaction features. So to transaction features, it is noting that what is fraud and what is not fraud. So that's how this brain is working. And there is one more thing, as I told you, this is memory is also called experience replay. So the gamer, it's just not learning from the latest moves. I mean latest patterns. It is writing down, like in memory we learn, we put in our memory, so it is writing down. It is, you can say, it is gamers notebook. So it is basically what is good and bad, and reviewing them randomly to learn better strategy. So that is happening. I think that's enough for that. Let's move. Okay, so let's move to the next slide. Okay, so the unfair advantage, why RL beats passive models. The thing is that I told you that these machine learning or ANN or CNN model, they are passive learners. They excel at the patterns through data sets. They're like students who have mastered a textbook. I told you that these are like they cram these textbooks, that this topic is on this page. They predict based on what they have seen. But our reinforcement learning agents, there is no if and but. Means like in fraud detection, there are no maybe decisions. So RL agent makes split decisions, either fraud or not fraud, based on the inherent value of the action, rather than relying on external threshold. So I told you this point, threshold doesn't affect its decision. I will show you in the production part itself. When we I will show that different thresholds affects the decision making of these machine learning and ANN and CNN models. But RL doesn't these threshold doesn't affect its decision. So that's why when RL agent makes a transaction, classifies a transaction as fraud, then human analyst got an alert that this is fraud. So uh, a human analyst can rely on that on a very high note, because RL agent is very highly confident on its decision. So the last point is active adaptation. RL continuously learns and adapts its playbook as a new fraud patterns emerge. I will show this in practical way also, because this is the bluff data set that contains some previous fraud patterns plus some new fraud patterns. So how to that RL, if we give update RL with these new fraud patterns, so it will not forget the previous fraud patterns. But that is a problem with these ANN and CNN models or machine learning models. There were they usually forgets the previous pattern, because they are they have decision boundaries. So we will see in production part. Okay, so moving to the next slide. Okay, so let's quickly move to the next slides, as we have to move to the production part. So yeah, this is the our winning strategy: the stacked hybrid model, two RL agents plus XGBoost as a meta model. So this is the our initial architecture. We have two RL agents. One is primary RL agent that focuses on overall fraud detection. Another is second one is residual RL agent, specialization in detecting hard to fraud patterns. Actually, the mistakes, there was some false positives that were not being rectified by the primary RL agent. So residual will rectify that and act as a second opinion or a challenger. So a meta model, I mean final model, is XGBoost. As I told you, this is the decision maker. It will learn from not from the data but from the opinions of these two RL agents. So the nuance advantage means that even the subtle change, very very small changes, even that the signals will be heard from the secondary model, which is our residual agent, and will be conveyed to the this final model. So this system showed significant improvement over our traditional models on our original datasets. Okay, let's move. Okay, so yeah, this is the critical slide. Okay, the proof, because it has the stats. So we have the stats of our all stacked models. You can see the performance now. See, if you can see here, stacked ANN. It means our artificial neural network model that I have again fine tuned it. So you can see here, zero false negative, no fraud missed, but there are 17 false positives. And with a stacked CNN model, there are with optimal thresholds, the threshold best threshold has been taken by the algorithm, I mean code. That's why zero false negative for both. But CNN showed 185 false positives. And this is the problem, because the these cases are wrongly told as fraud, but they are not fraud. Similarly, with the ANN model, 17 cases are being disposed as fraud, but they were not. But look at this score now, perfect, 100%. For Yeah, so for our stacked RL model means two RL agents plus XGBoost model, false positive zero, false negative is zero. Can you believe it? I mean, I told you in that original opening script that into the production part. I will show you. Uh, why it is written that we have done some correction, because there was initially a function problem which was conveying wrong probabilities to the final model. That's why the final model was overriding for some transaction, was overriding the decision made by the second model. So this requires domain expertise. Only subject matter experts can do that. So I will show this performance now of everyone uh, in the production part also. But here also you can see, here I have pasted the metrics. I mean classification report. You can see here 17. I showed you 17 false positive, zero false negatives for ANN stacked ANN model. Stacked CNN model 185, the large number of, because optimal threshold doesn't works in real environment, in real world scenario, when when you're making prediction on real world scenario. So actually the default threshold works, or some auto threshold function if you have created. So 185 false positive is very big problem, a lot wastage of time, even though there is zero false negative, no fraud was missed. But it will take ample time for analyst, human analyst, to operational time will be waste. But here you will look at our stacked RL model results: zero false positives, zero false negatives. Can you believe it? Because this should be the final outcome, because this is trial and error. So this is split decision, I told you. uh, Probabilities doesn't threshold doesn't affect the model, and it goes for split decision. So let's go to the production part. Okay, so here we are on production part. So you can see here prediction code for stacked model, that is our artificial neural networks, two artificial neural networks plus logistic regression. Logistic regression is the final model. I told you this is the fine-tuned version. So because you can see here on last time there was 491 and one fraud was missed, but not this time. I will run this code in front of you, so it will run from start now. First, this is the two data sets are there: original credit card data set, and I told you the bluffed transaction data set, which have some few frauds, which was on training part, but few new patterns are there. So this code will use the best threshold, but this is not recommended in, I told you, in the real world it is not recommended. But still we have we have to see the performance, best performance for all three models. So that's why I will show the auto threshold, default threshold also. But let's first hit with the optimal threshold. Okay, I'm running this code now. It's okay, so it's started running. The output will be shown live. This is live, and output will be shown live here only in the output console. That will just come at any time. Yeah, okay. So see, loading base NN models, base model 1, base model 2, meta model logistic regression, and then now the model is loaded, and pre-processing complete. Total fraud case 492, and we will check how much it identify. I mean, I already showed the metrics to you, but this is live. I'm not making this up, so that's why I always show the live part also. Generating predictions from base NN models on these original credit card CSV file. Okay, so yeah, now generating final probabilities from the final model, that is our logistic regression model. Base models have already generated predictions, as you can see, and now the final predictions with the our final model logistic regression. Just remember, this is using the optimal threshold, not default threshold. That is zero point 0.5 means 50%. See, same results. Wow, zero false negatives and 17 false positives. Let me expand it here. Wow, this is the power of these. They cram the pattern. So I fine tuned it. So this time, no, even last time one fraud was missed. This time zero. And optimal threshold you can see here, 0.84. The code has chosen the optimal threshold. Else, I believe these false positive will be more. But still, the main goal is zero false negative. So no fraud was missed. But here also in big picture, you can see 17 false positive, zero false negative. But for the bluff transaction, you can see here, in this bluff data set, there was blood transactions are 200, means fraud transactions are 200, 1000 are total transaction are 1200, 1000 are not fraud, 200 are frauds, but they are mixed frauds. So how many it has captured, you can see here, it has captured 42 frauds, and 158 is missed out of 200, but there is no false positive, means there is no transaction with it has said that it is fraud, but it was not fraud. So the and the optimal threshold is 0.01. This is the problem. Optimal threshold, I have seen you for demonstration purpose, but we cannot go with the optimal threshold. 0.01 is totally not justifiable in a real world scenario. So but to make the demonstration of a best performance still now, so 42 fraud transactions are being recognized with zero false positive. And now I will show you the same with the default threshold. When default thresholds comes, then what will be the performance metric. This is the same model uh, that we I just demonstrated above. This is the same model, but now it will work on default threshold of 50%. Above 50%, that will be treated as fraud. Okay, okay, let it go, let it go, let it go. Prediction generating from the NN models. Firstly, base model will generate the predictions, then final model will generate the predictions. I mean, final prediction. I was just, want to show, yeah, greater than equal to default threshold. So default threshold is, well, I mean, if 50% equal or above, then only. Sorry, I told you above. So there is equal sign also. So equal and above, 50% will be treated as fraud. That is the default threshold for every model. If you don't put like manual threshold, then all models will treat 50% as a default threshold. So see, what happens is, even though the model is extremely good at caughting all the frauds. See, I'll just expand to explain you in a better way. See again, zero false negatives, no fraud was missed, but from 17 to 23, fraud positives are increased. Here also 23 0. So this is the problem. Default threshold is 0.50, greater than equal to 50%. So the threshold, that's why I told you that for these machine learning ANN or CNN models, the threshold is a problem because it affects the results. So for the bluff transaction, same. You can see 42 was caught, 158 are missed. These are the frauds that are missed. But the main thing is that no false positive is there, but this should also be zero. So but because they are not trained on those new patterns, that's why this is the performance metric that by default threshold. Okay, so we will move to now CNN model, stacked CNN model. It has two CNN model as base models. I told you they are image processing model, but we converted them, we trained them with for data with some feature, and again logistic regression will be final model. Let's see the stats for that. Okay, so this is the code for CNN model. Retrain to CNN plus logistic regression as meta model. I mean stacked CNN model. So I retrained them, and let's hit the code without further ado. And again, this is image processing model. I converted it to fraud model. See, loading retrained CNN meta model. But this is again optimal threshold. Then I will show with the default threshold. So optimal threshold, so it will the code will go for the best threshold, where the count for fraud positive and false negative is minimum. That is the main thing. So you can see here again same credit card data set. 492 are the fraud case. That's why total fraud cases in original credit card CSV file 492 presented prediction from CNN base model. Similar pattern, I mean similar steps. Firstly, base models will make predictions, and then final model will make predictions. Okay, so wow, see, meta model input feature shape this and generating final probabilities with logistic regression meta model on original credit card CSV file. So within a few seconds, few time, I mean, we will show the report, classification report. But this is with the optimal threshold. But remember, in real world, there is no optimal threshold like this because we don't know which one is fraud or not fraud. Right now, it will check because there is already historical data, so we know which is fraud and not fraud. See, 492 are all fraud cases. Will let me expand this and then explain. So all 492 cases are been caught. That's why zero false negative. But there are large number of false positives. The system says this is fraud, but 185 cases are not fraud. So this is the problem. Yeah, I told you, a lot of operational time will go waste when analyst if these alerts are there, and and for the bluff transaction, I mean from bluff dataset. Again, same model stacked model ANN model results are same. 42 transactions are being caught, 158 are left because 158 these are also fraud that are not been caught by this model. Same performance of that our ANN model. See, even with the default threshold it was 0 42, I mean 42 and 158 and 0 false positive. Okay, so yeah, same with the optimal threshold for ANN, stacked ANN and stacked CNN model. Same, 0 false positive, 42 caught, 158 left. Now I will show you this CNN model with a default threshold. Okay, so this will show you why default threshold is important, because in real world we cannot go for high threshold. See, generating prediction from this will take time. In the meanwhile, okay, we will wait for the that generating predictions. Okay. Okay, so wow, so these are results you can see here with the default threshold. Let me expand this for to explain. You can see here why default threshold of 0.50 is 50%. Now there are significant decrease in false positive. Now 65 false positive, but from zero false negative becomes four. Means four fraud cases has been left, has not been detected by this model. So but significant decrease in this. But that's why I told you that default threshold is usually being taken, because in real world we cannot take 85%, 90%, or something like optimal threshold as. Okay, so yeah, we cannot take the optimal threshold as a uh, threshold in our real world scenario, because you can see here in this optimal threshold is 0.84. So equal and above this will be treated as fraud, and rest will be not fraud. If I see the condition, yeah, yeah, yeah. Okay, okay, cool, and you can see here, yeah, greater than or equal to optimal threshold. So yeah, above than 84 or equal to 84 we will treat it as fraud, and that less than that will be treated will be classified as not fraud straightly, because these threshold you have to give by default. It's 0.50 or zero point 0.5 means 50%. So in this scenario, if you have taken 0.84, then less than this till 50% means, if there is a probability of more than 50% and less than 84%, those cases will be missed. In if we deploy it in this in real world scenario. And let me show you, I have a detailed diagnosis of these thresholds. I cannot run because it already being ran on the same file. So original credit card file, I put different thresholds on test. So see, 0.01, 0.00 means 1%, 2%, 3% till 99% for this credit card file. So here you can see here, whenever threshold from least threshold from 1%, false positives are maximum. But whenever we are going towards the higher thresholds, it is becoming less. So from here on onwards, 0.83 it's become less, 17 false positive and 0 false negative. So system choose 0.84 as the optimal threshold, because after 83, then 84, then there was no significant improvement, because the same stats are there, 17 0. So it goes for a one step ahead. I mean, 0.83, it is also 17 0, but it took as 0.84 as the maximum, I mean optimal threshold. But in real world it cannot be happening. This is why I told in PPT itself, they cram this historical data. This model was trained on the same data, synthetic data created from the credit card file, so that they crammed the pattern. That's why they are so good in making these false negative 0, and false positives only 17, with the optimal threshold of 84. If system has taken 84 with its own logic. So you can see here at 0.50, it's not bad, even to 23 false uh, positives. Means 23 cases are recognized as fraud, but they were not. But there are zero false negative. So I mean, no fraud was missed. But the thing is that in real world, it will not happen. Real world, we have to take the 50% threshold, because if we take 84% threshold, then what happens, I will tell you. See, this is the optimal threshold. You can see that why we should not take as optimal threshold of 84, because in real world what happens, this similar pattern will not be there. So what will eventually happen, so some features will be up and down when the transactions will come of fraud. So this probability will fall from 84, it will go to 76, 769, might be 58, might be 54. So what happens, because there will be not so similar patterns, so on similarity this threshold generates. So when there will little bit unsimilar pattern, the probability will fall. So that's why in deployment, usually the auto threshold of default threshold of 0.50 is being taken. So that's why I told you, in real world scenario, we cannot go for optimal threshold. So for judging the model for its optimal performance, the default threshold of 0.50 is being taken. So in this case, you can see here, even yeah, this is 23 false positives and 0 false negative. The system make the false negative 0. So that is the main case. The fraud is not being missed, but we are good with the default threshold. And similarly, with block transaction, the system was able to find 42 fraud transactions. So similarly, if I show here, you can see with 50%, as a default threshold, CNN stacked CNN model is showing significant performance of 65 false positive only, and four false negatives. But with optimal threshold, what it was showing like this. See, 185 false positive, and optimal threshold is 0.02. Can you believe it? 0.02%. So this is not justificable at all, because I put the condition that took the optimal threshold where false positive and false negative will be minimum. So it went for this only, that zero is the minimum, and with zero this number was the minimum. So optimal threshold is 0.02. But in real world we don't have to we cannot go with this. So 0.50, even 65 false positive, far very significantly low from last count, and four false negatives. So, and again same performance like ANN 42 was caught in bluff transactions. So we will see our RL model now and performance, and let's go. Okay, so here we are on coding screen, and this is our primary RL model prediction code, and yeah, the same I showed you in the PPT. Let me show you. Wait a sec. Okay, so if I expand this now, yeah, you can see here what happened is, this is primary RL agent. So this will produce the prediction, and this is our secondary RL agent. This is residual RL agent, I have named it. So this will give its prediction, and then the meta model, final model XGBoost will make the final fraud decision. See here, why? Because this is the prediction code. So this prediction code produces this result, 19 0 false positives, and sorry, 0 false negatives and 19 false positives. So what happened that performance was stuck at 19 0. So that's why I need another model, this one. I put those 19 false positives in data, training data. I mean, made a training data out of that, synthetic data created out of 19 false positive, and other fraud cases as well, and trained the model. So that's why the performance will improve, because I want to outperform that ANN and CNN model. I showed you performance of them. See, by default threshold, it 23 0, but I took optimal threshold to show you, because I need to show the supremacy of RL agent. So see, 17 0 by optimal threshold, that is not recommendable in real world scenario, as I explained. But till single primary model performance is 19 0. Okay, this is split decision. Okay, as I told you, all the functioning, and for that bluff data set also, it caught 42 transactions, similar with the both ANN and CNN model. CNN was also caught 42 transaction. So because these transactions were on on training data, so RL agent also caught this. But what was telling you, that after 19 0 the performance was stuck. So what happened next, that I further fine tuned it. So when I further fine tuned the model, I will show you this. Okay, so I was able to corrected till 14.0. So see, I must have written over here. Fine tune further using log transformation and let XGBoost understand meta feature more precisely. So what happened is, I made some transformation so that final model will understand it. So further, I came down to 14.0, but with the help of another model, I told you here, with the help of this model, uh, we bring to 14.0 with the help of residual model, secondary model, and meta model also. This time we come to the as 14.0 on our credit card data set, much less than 17.0 of with the optimal threshold of stacked DNA model. So we outperformed it here only, that we got 14.0. But we have to initially, why because the question was that why 14 also still when I have trained the secondary model also. So I told you it requires domain expertise. See, after intelligent rule based correction, I was able to, correct it, and then what becomes the result? Zero 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 false positive, zero no, false negative. So absolute, you know, absolute carnage. I mean, outperformed everyone. But this I will put this code to show you because I'm not making this up. See, this is the same way the primary model. This is our primary model. This is our secondary residual model. See, primary RL agent, residual RL agent loaded, and then winning execute meta model loaded. This is the file name. This is has been loaded, and it will make the initial prediction. This is all live in front of you. So that's why when RL agents are acting and with the meta model. So when these predictions are being made, and human analyst can rely on the decision because it is very much confident on the decision, and I will show you why. See, first let the result come. The same result I showed you here in PPT itself. See, 0 0, and it's going live here. Oh yes, the results are there. So yeah, you can see here the results will come anytime now. Initial prediction generated, applying correction. This require domain expertise. Subject matter expert can do this. I will tell you the full diagnosis because those 14 false positive I showed you earlier should be rectified, but there is some problem with the function. It was not generating correct probabilities, converting the q values to probabilities. It was having a problem, and the incorrect probabilities were converted. So that's why, as a domain expert, that if your secondary model is giving a right prediction, then why those 14 positives are still coming. So we have applied the rule based correction, and anytime this result will come now. See, classification report. Oh wow. See, similar stats, 0 0. All fraud cases are identified. All not fraud cases, front not fraud cases are identified. This is nothing left. This equation is properly balanced. 0 0. Wow. Can do someone do that? And on that beloved data set, still same stats because these 42 were present in training data. So similarly with ANN and CNN, this RL stacked model was able to identify it. Okay, zero false positive, 42 was caught, but 158 were not caught. Okay, just I will tell you further. Uh, uh, what was the problem that we know we have to do this correction. Okay, so yeah, before going further on those, diagnostic, I will show you firstly the what the thing I told you, threshold testing from primary RL model. So this is our primary RL model. See, same file, model file. So this R the threshold doesn't affect the RL agents. Let me run this code in front of you. If you think, because I have not made this up, and you can see. I just ran that code and is running. Loading primary RL model. RL model loaded successfully. Evaluating primary RL model on credit card file. So it will show the different thresholds similar to this one, like this. I told showed you, for ANN stacked ANN. Values are coming at any time right now, and you can see here. You can see threshold, different thresholds. This is tagged in. So different thresholds will affect the output. 36.0, 26.0, and 25.19 initially at 80, after 83 and 84 similar results. Then again also the same similar results, but it affects the threshold. As I told also, in real world scenario, the threshold will be at 50, because your different pattern, the threshold will be up and down. I mean, fraud probabilities will be up and down. Let's see here. For this primary error model, I will show on meta model also, but meta model is made up of two models, and then this one XGBoost model. So initially, we will testify on the RL primary model itself, because the thing is that it doesn't threshold doesn't affect its split decision. And even for meta model I will also show, because we have to choose a default threshold for this meta model XGBoost, because at if we change the 50% threshold, then also the performance will degrade. Let me show you first that primary RL model, that RL agents doesn't affected by any threshold. See, oh wow, I I told it and it gives the results. Maybe it is obeying me. See, at the credit card thresholds, performance of primary RL model across thresholds on credit card file. See, at 1%, 19.0, at 2%, 19.0, at 3%, 19.0 till end, 99%, 19.0. Even on bluff dataset, same. At till 1% till 99%, same. Zero false positive and 1 for 58 false negative. See, I was not making this up. Across all thresholds, same results. So it goes for split decision. You can rely on this. This is trial and error. I told you, this is active learning, and this one is passive learning. So, but these early agents are very stubborn to train upon. It took me 3 months. Initially, 1 week I was not able to put them on train. I was not able to formulate the policy. Okay, so next. Okay, so yeah, so quickly we will see. Firstly, that those 14 false positives for deeper analytics. I have already ran this code and checked. Why we applied those rule-based correction. So this is the output screen. So the thing is that the RL agents are working fine. They are not making any mistake, because they are I told you they are go for split decision, and they are a trial and error They never make mistakes. So what happening was the meta model, our XGBoost was making mistakes. So see, identified 14 false positive transaction in initiating detailed analytics diagnostic for false positive transaction 1. So particularly you can see here for this transaction, these are the values. I mean, this is the transaction, features and values. Features are from this and amount and this time and all other features. And what is the outcome? Primary RL agent output. See, Q values. It generate Q values. Class 0 means not fraud. Class 1 means fraud. So primary RL agent is saying that 2040 value for not fraud, 3644 point something value for fraud. So this value is higher. So predicted action, the prediction becomes fraud because the predicted value for class 1 means fraud class is higher than the not fraud class. So it says that it is fraud. And I trained the residual RL agent to correct that because the false positive should be correct. So it checked those transaction and it says for class 0, not for class, the value. Look at the value. Look at the Q value. It is in, so much. If I count, this is so much big value in term of these two values. So even for the fraud class minus. So initially, what is the action? We all know that this is high Q value. This is in minus Q value. So it means it is saying that this is not fraud, class 0. So 0, not fraud. So now it becomes conflict for the meta final model because this final model has this softmax function is there which converts these values to probabilities. This has problem with this function. So agents actions conflict because conflict, yes, this is conflicting because our primary agent is saying fraud and our residual agent is saying not fraud. So this is softmax problem, a direct conflict between the agent's top predictions. The XGBoost model, the final model, however, makes its decision based on the confidence score. So the thing is that this is softmax problem. So but now what final model is doing, it is going for difference in the Q values. See, when we primary model, Q logit Q difference becomes 0.50. Confidence, you can say confidence score, around about 50%. And if we convert that to our secondary model, it's become 0.02 something, means 2% only, 2% something. So there is problem. Now, even though there are so many high value between not fraud and versus fraud, which is clearly showing our secondary model saying so much high values difference, q value difference, and saying it is not fraud. Then also these when a transformation has been done, the confidence score for primary becomes higher, 50% versus 2%. Then final model is saying that the probability becomes 98% for fraud because only 2% is there the confidence score from the secondary model, which is wrong. So this is we have to correct. And for all 14 transactions, see, diagnostic for false positive transaction 2, this is the whole transaction features. And you can see here again same primary RL agent, our first model is saying 2041 point something value for not fraud and fraud 3644 something. So any layman can say that this is saying that this goes for fraud, high value for fraud. So that's why outcome is fraud 1. But then again our secondary model residual RL agent is saying that this much value for not fraud, this minus value for fraud. So always positive value wins and between minus and plus, and there is also a huge difference. And you can see here, so that's why not fraud. But then again there is a conflict because one is saying fraud, another is saying not fraud. Then there is confidence score is becoming this one again, 50% for primary model, and for that 0.01%, my means 1%, 50% versus 1%. then again the probability is going towards the higher model. High model, I mean the highest confidence, the model, which model has having, so fraud probability becomes 94%, so it is uh, predicted as fraud. Or okay, so yeah, so you can yeah, understand, you must have understood now till now, yeah. So the thing is that even after the conflicting signals for different transactions, like you can see here also, 50% confidence score, 31% confidence score. So there is conflict between uh, these predictions, and there are difference between the confidence score, but still somehow this XGBoost is drifting towards the fraud. So every time with these 14 transactions particularly, the same thing is happening. You can see here again, fraud, not fraud, and then this confidence score is 50% and 14%, and then there is a conflict between the both predictions, and then again it is drifted towards the 96% fraud probability. So there is absolutely definite pattern that when with this type of error, because our residual model is able to find these transactions as not fraud. So what is the proposed you can see here, conflict analysis and XGBoost softmax problem. Agent action conflict. Yes, they have conflict. Why? Because if for these 14 transactions, primary agent is saying fraud and residual agent is saying not fraud. This is softmax problem. A direct conflict between the agent's top predictions. The XGBoost, our final model, however, makes its decision based on the confidence score. The confidence score is this one, the logit Q differences that I have showed. For you can see here, 50% something, 40% something. So the predicted probability becomes 78%, so it will classifying it as a sample example. You can say it will say fraud. So what is proposed? Rule based correction is proposed. And what is rule based correction? If the residual ARL agent predicts non fraud, override the XGBoost prediction. So current XGBoost prediction is fraud, and corrected final prediction is not fraud. So that's why we went for that rule based correction. Okay, so okay, let's quickly check this out. This is threshold check for stacked model. And I will tell you that I already showed you that threshold doesn't affect the RL agent models. So similarly, this is for our final model. We put different thresholds. So I told you that zero point 0.5 threshold last time, 14.0 was the performance before the rule based correction. So if we change threshold, the performance will deviate. You can see now it becomes 12, but the false negative started increasing. 1 at 70%, 10 false positive, but 3 false negatives. At 80%, 8 false positives and 8 false negatives. At 90%, 6 false positive and increase in false negative. These mean these are fraud cases that are being missed. So we cannot go for any other threshold than the default threshold zero point 0.5. That will work best with the that is working best with our final model, that is XGBoost meta model. Okay, next. Okay, so yeah, so as you can see here on the bluffed data set, the performance was with every model was same, that they were able to caught 42 fraud transaction, but they were not able to caught 158 fraud transactions. So what next? So the thing is that I told you in the PPT itself, that we can enhance this model, RL model, but it doesn't affect them. I mean, the policy will not change even with the new data set updation. So if I say if I say that this bluff data set, which is having 1000 not fraud records and 200 fraud records, take it as example that this is the real data set in real world. So we got a data set which has today we got some 200 fraud transactions. So we want to update model with that. So that problem is that with machine learning, ANN or CNN models, they will, I told you, they will learn this, but they will that have problem with recalling the previous data set, that was that credit card data set, that they will having problem, they will sudden forget the old predictions and mix up the things. So this is not the problem with the RL agent, and this reinforcement learning I will show you. Just see what I have done. I have created a blended RL model. I could have updated these primary model or residual model, but for demonstration, I made another model out of it. So with this code, you can see here now. If I show the output console in use, you can see here loading pre-trained RL model. So same model, our primary model, RL before fine-tune model, pre-trained model loaded successfully. Okay. So what happens right now that yeah, model weights loaded from this model. This is our primary model, same model. I will show you here. If you want to see in any code what is our primary model, see, I'm not making this up. See the path. RLv4 fine tuned, check, I mean, see here, RLv4 fine tuned on synthetic. RLv4 fine tuned on synthetic. See, same primary model. Those model weights they have, are loaded from that model file, and now we will, pre-trained RL model is loaded, and that will be updated with these new records. See, total record 1200, total fraud cases 200. So initially the model went for training, and in the end of training we achieved what you will see. Final phase 2, final evaluation of the best model. And the best model is, oh my god, see again, 0 0. What we have done in training, true positives 200 from 42. It was having problem, I told you. Only 42 cases were being diagnosed, caught. See, this was the matrix na. 42, 158 was left. So now our new RL model that I have updated, it successfully caught all the 200 fraud, and successfully classified all 1000 not fraud cases as not fraud. So we will deploy this now, and we will we will I will run this code, and you can see that how from old to new the performance increases. See, phase 1 old stacked model performance, this is old stacked. The same model performance told you, 0 false positive, but 42 fraud and 158 missed. Here, see, phase 2 new blended model on bluff data, that particular data set. See, wow, 200 fraud cases caught, 1000 not fraud cases disposed as not fraud, and 0 and 0 here equation. See, false positives 0, false negative 0. So this it applies our point, active learning. RL continuously learns and adapts its playbook as new fraud patterns emerge, making it inherently more resilient to evolving threats. See, I was not making this up. You can see here, even I put 0 0 matrix, same matrix I showed there. And why this is our next frontier? Because it learns new pattern, and actively we can update this to our uh, uh, this one, to the old model. We can update new fraud patterns to the old model, so that it will be updated. So in future, what I have I was telling you that we can adapt a new layer. We will use uh, that model, this one, uh, I will tell you this one, isolation forest as our stacked system. We will use isolation forest as our this one. unsupervised algorithm. So we remain step ahead of the evolving fraud landscape. But I have showed you example how to upgrade with the new dataset. Right now, I just showed you. So this is not just a model; it's a dynamic, intelligent defense system that safeguards your assets and reputation. So just quickly, I will show that you know what reinforcement learning. It is not a simple thing. I will tell you. You will have to work very hard to train these RL agents. So it was introduced in 1989 by IBM. It was the first TD gammon game that uses that temporal that RL technique was temporal difference. In 2013, Atari games were there. The company was DeepMind. Now it's been uh, acquired by Google. It was first time the Q network was there with trial and error. And now in 2025 ASR, that's me, okay, my initials, and I made this fraud detection system with stacked RL, two RL agents plus XGBoot, and yeah, this trial and error. So this is very very hectic project, but the last thing is there. I will show you the email part and email alert part with this model prediction as well and sample predictions as well. So next. Okay, so yeah, I showed you the results. Precision recall rate all 100% and accuracy 100% achieved. Whenever we want to update the new data set, we can update, and it will the policy will be updated, and this does not affect the previous predictions. So now the prediction part, I will show you that I have made manual prediction on small sample of unseen data. This is for demonstration purpose. I will also show the live demonstration of predictions. But firstly, I will show you that I have manually created this data set. Only six records will be there. The three are fraud, and three are not fraud. Let me run this. So what is happening is we will generate this record file, call record file from here. Sorry, this transaction file from here in Python, and we will generate the alerts from R, because Python libraries are some libraries used in this code. Are native to Python, so it's better to generate alerts from there only. So see, this CSV file is ready for R, and these are manual prediction process complete. I will show you the that file also. You can see here, if I go to the directory, default directory, then the latest file will be in the end. See, this is the file. I'm opening it in front of you live, and I have created it. See, because I have added the credit card number, so we will generate the alerts on credit card number. And you can see here what is the prediction. These are manual prediction. Three cases are disposed as fraud and three are not fraud. So initially, these transactions should be caught, because these are transactions for the same credit card number, and starting with 1 2 3 4 ending with 3 4 5 6. Okay, I will close now, and what I will do, I will generate from here, because I updated that in task scheduler. Very very friendly. I mean, very very user friendly interface of window, and R is totally we can integrate R very comfortably with it. So firstly, I will go to email window and clean it up, so that we can have fresh alerts in front of you for live demonstration. Sorry, we have to go to task scheduler, and you can see here I will just run this. So, and we will wait in the email window to arrive. Okay, so This is something, as a subject matter expert or data scientist or fraud manager, you have to do that. You have to put your all your experience and expertise in this alert generation, because without a good insight, without the good conveying of what you want to convey to the human analyst who is sitting over there, this is not possible. So wow, see, the alert came in live in front of you, urgent fraud alert. This is the time for this card, urgent fraud alert, August 10 to 2025 at 7:21 a.m. Wow. So if I open this now, wow, you can see. I told you that R has a capability of very stunning visuals and dashboards. So let me read this fraud alert. I already read the subject line for this card number. Hello team, an RL ensemble model detected a potential fraud event for card number. This transaction time. This will be the always the last transaction time, because this is cumulative based alert. I made a single rule for demonstration. For one transaction also will fire for cumulative value of $300, and even if the multiple transaction is there, then also will fire. So the transaction time will be always the last transaction time. So okay, cumulative horizontal transaction exceeded the $300 threshold. I told you. So you can see here transaction time, suspicious transaction summary, card number this one, transaction time January 1st, January 2025, night 12/1/42, $100, model verdict, potential fraud. Second transaction, again at night 12/3 at 20 seconds, $250 potential fraud. And then third transaction at 12/5, $700 potential fraud. See, wow, what a beauty. So this should be, the clear insight should be there. Firstly, the total amounts that are being captured, and what is the amounts, and what is the model verdict. And you can see here it is a plot also. So attached plot shows cumulative fraud progression. Now if I click this, see the analytics. I told you now in the PPT itself, in-depth analytics. See, wow, what a beauty. Can you believe it? Cumulative amount of fraudulent transaction. RL ensemble verdict. Threshold $300. Verdict fraud. When analysts open this, and when it checks the data, that analytics, I mean, you can see here this red dot shows the threshold line of $300. This is exactly between 200 and 400. This shows the threshold line. So first transaction went for this, which is under 200, and second transaction, when done, it crosses the cumulative threshold of $300. That's why the alert will fire. But when alert will fire, third transaction also happened. So you can see here, if I just for demonstration purpose, if I have a snapshot of this one, so I can tell you better. See, I will just have a snapshot of this one, and I will tell you what's happening over here. That what human analysts will say, wow, that now. See what happens when the first transaction was done of $100 at 12 in the midnight, 12/1/40. So it was of $100. So that's why it shows here less than 200. So $100 is here. So these values are automatically populated. So the agent knows that first transaction was at of $100, and then second transaction was 250. So the sum becomes 350. So the sum becomes 350. That's why this star is here. This second transaction which is showing. It is just showing that it becomes 350 here. So when it becomes 350, it crossed the threshold of $300 value. So the alert will have to generate. It has to generate. But in the meantime, the third transaction will also happened, because data came late, and the third transaction was also done. So it is also being captured. So now you can sum it up: 250 plus 100, 350 plus 700, 1150. So see, that's why this third star is showing that the above 1000. It's 1150. So when analyst knows that three transactions in quick succession of time, and this is the final impact that fraud, the cumulative value becomes 1150. So wow, it will understand that I have to take the corrective action right now, because this has been when RL model says fraud, this the first thing is mind that this is a very high chance that this is fraud, and then this in-depth analytics tell the human analyst that you have to take the action, because I have not taken any action right now, because it's totally upon to the management. We can we can initiate, but I have not, for demonstration purpose, I have not taken any automatic action. We can automate we can temporarily bar this card. We can initiate call, or email on the numbers that this transaction has been disposed as fraud by our system. So we can do a number of actions, but it's totally upon to the management or the company. So but I was telling about like an SME, subject matter expert, or fraud manager, or a data scientist, or a data analyst. You have to put these insights, you have to convey these insights to the human analyst who is sitting and receiving these alerts. So this is a clear picture right now, you can see. But this is this was manual data I created for demonstration purpose. But what I will do, we will go back to the Python code itself, and see, and we will use our stacked model now. Same 2RL plus XGBoost model, and we will take the real transaction from the credit card dataset. I have taken six transactions again, but this time the real transactions. And we cannot use these model on only six records. We have to process the knowledge. We have to take the knowledge distillation process, because when we train these models, they were absolute having a very high data, synthetic data. I don't know, maybe more than 4 lakh transactions were being trained upon, these models were being trained upon. So we cannot process small transaction like these six transactions. So what we do, there is a method called knowledge distillation. So knowledge distillation, the this is teacher model, and we will train a student model on the same behavior, so that it will mimic the behavior of this teacher model. So okay, so we will use this example too. Even for example one also, you can see here the known class was this one from the real credit card data set. These transactions, these were not fraud, and these were fraud, and they were quickly they were correctly identified by the student model. See, not fraud, not fraud, not fraud, 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 same. But we will use this example too, because in this I have taken random samples from fraud and not fraud class, and that is the more main thing, that when you took random training record for both fraud and not fraud class, and then train the student model and then predict. So see, again prediction was same, I mean correct, for all six transactions. But we will we will use this one, uh, loading teacher model. So what it will does, it will create uh, create the data set also, the real data set, just and the real predictions. So the records are real from the credit card data set, and the prediction are real from our teacher model, that will train the student model, and student model will make predictions, and then we will use the credit card data set. So see, so what happens is that that file that I told you, now it is being replaced. Okay. So if I go here, so see here, replaced, it will the same file, but it is being replaced. You can see here 734 and 735 is there. So this is being replaced, and now just we will run the again the same code, our code again, and now we will have the new alert. But this time with the real transaction that we have, just credit card number will be added because we need a credit card number to generate alerts. But again, you can see that we will have the same analytics, insightful analytics for the human analyst to judge. And this time, these are real transaction from the real data set. See, wow, urgent fraud alert for card number. This one. If I open this again, hello team, an RL ensemble model detected a potential fraud event for this card number. Transaction time. This one. Cumulative fraud transaction exceeded the $300 threshold. Here is the summary. Below is the summary. Suspicious transaction summary. So first this time 456.12 potential fraud. Time is 4:28:00 second. 4:28:09 second. $575 potential fraud disposed as. Then at same date 2 January 10:18:45 $3,502 potential fraud. See, now if I just take this screenshot for comparison. Let me, yeah, okay. So here this is, and here is our alert, and I open this plot now. See, now again when the human analysts see cumulative amount of fraudulent transaction, RL ensemble verdict fraud threshold, this one, okay. And now see this, this is from the real transactions of that telecom, that Kaggle from Kaggle.com. You can see here when two transactions, when the human analyst will see that the first transaction initially put is gone beyond the threshold line of $300. It means the first transaction itself is more than $300, so the alert would have fired in the first transaction itself. But till the processing, the two transaction also happened. So but this, look at this chart, this bar line, I mean, yeah, look at this line, transaction line, sorry, one after another simultaneously. And if I show you the transaction time now, so now $456 something happened at 4:28:00. What 4:28:09 second another happened, 575. So in a split fraction of time the two transactions happened. This is dicey itself. But what happened is, already model has caught the fraud and potential fraud has been declared. So 456 plus 575, it becomes more than 1000 something. So here you can see here when the second transition happens, more than 1000, and then sudden spike for 1000 something plus 3000 something, it becomes 4500 something. So right now see, more than 4000, 4500 something, it is aiming at this third transaction. So this is the impact right now. So this is the insight that should be conveyed to the human analyst by any SME or fraud manager, that oh my god, this is the impact right now, $4,500. So he will check whether the automated action has been taken or not, or what is the SOP or SLA it has to, the human analyst has to follow. What is the standard operating procedure? What is the our agreements? This is something very insightful, and this is something uh, should be in mind while while making these alerts. So I told you these RL agents, that they are the best thing that has ever happened. So that's why they are part of deep learning. And I put all the highlights. I put you credit card classification via RL agents ensemble model. So primary residual XGBOOST and meta model, I explained all the steps. Fine tune models comparison I showed you. And Then comparison on real credit card and bluffed I showed you, and RLL demonstration where this alert making I showed you. Future roadmap I told you that we can have the isolation forest as a future roadmap, and what what we can do is that we will see which transactions are contaminated, because isolation forest separate those transactions from the similar transactions, and for those transactions we will use our stacked RL model, and we will see even the frauds we will of course we will analyze, but for the not fraud also which low confidence score we will check. So that's how we will come to know that what is a new pattern. So I thank you all for your time and attention. I am confident that this reinforcement learning, powered fraud detection system represents a significant leap forward in protecting the assets and enhancing our customer experience. This is something we can put that to the client level, or if we have a managerial PPT presentation, I mean high level presentation. So guys and girls, this is Akhil Singh Rawat signing off. Please take care and have fun. Okay, bye bye.